In this presentation, I will talk about simultaneous equations. This is when we have more than one equation that are related to each other. The outline of this presentation will be first to provide a definition for simultaneous equations, then to talk about simultaneity bias, then to review the two-stage least squares estimation for simultaneous equations, and finally to provide testing for the rank condition. So what are simultaneous equations? Simultaneous equations are estimated when at least two variables are jointly determined. So the most frequent case is when we have two variables that are the outcomes of a system in equilibrium. So as examples, we could have supply and demand equations for price and quantity that are jointly determined. So price determines quantity and then the quantity determines the price. Or as we're going to have the examples later on, we can have labor supply and demand where the hours worked determines the wage, but then the wage determines the hours worked. So they're both jointly determined. So simultaneity is another form of endogeneity, and as we know, endogeneity would produce biased and inconsistent coefficients, and therefore we need to make corrections for it. So simultaneous equations can be estimated using instrumental variables and two-stage least squares to correct for this simultaneity bias or endogeneity bias. So where is this simultaneity bias coming from? So first to start, let's discuss structural equations. So here we have a variable y1 determined by y2 and an exogenous variable z1. And then we have y2, which is the other endogenous variable determined by y1, which is the same as this one, and then an exogenous variable z2. So what we have here in these structural equations is that we have two endogenous variables, y1, that's a dependent variable here, but independent variable here, and y2, which is a dependent variable here, but independent variable here in the first equation. And then we have two variables that are exogenous and only occur in each of these equations. So structural equations basically would have these endogenous variables in here as well. So in order to show the simultaneity bias, let's insert the first equation y1 into here. And then, so here's the second equation. This is the expression for y1 right here. And then what we're going to do is we're going to open up these parentheses and collect the terms. So here y2 is happening right here. So we're going to put it on the other side of the equation, and that's what we have here. y2 times 1 minus alpha 1 times beta 1. And then this is the new intercept. This is now the coefficients on z1 that we have. Alpha 1 times beta 2 is the coefficient on z1. That's still the coefficient on z2. And this is now the new composite error term. So now let's divide all of the terms by this expression. And that's what we're going to get here. So even though this is long, here what this is showing is that y2 here would be correlated with the error term u1. You see this? Because u1 is determining y2 now. And so if we go back to the original equation, we have that y2 is related to u1. Well, that's not good because we have endogeneity. And this is basically the simultaneity bias that we have. So y2 here would be endogenous in the equation for y1. So now if we have this long equation, we can rename the coefficients and obtain the reduced form equation for y2 because This is all a new intercept. This is all a coefficient on Z1. This is all a coefficient on Z2, and that's the new error term. And so that's what we are finding here. And the reason why we're calling this the reduced form equation, because we only have exogenous variables in here. So notice that we do not have the endogenous variables here as independent variables. And so again, the structural equation above here would produce bias and inconsistent estimators because Y2 is endogenous and related to this error term. But this reduced form equation would produce unbiased and inconsistent and consistent estimators because Z1 and Z2 are not correlated with the error term. They're exogenous variables. So the same procedure can be applied for the other equation, and we can show the same simultaneity bias for the other equation as well. But um, the point here of this slide is that from the structural equations that we started here with the endogenous variables being in here, we derived the reduced form equation that only depends on exogenous variables. And we are also showing that if we estimate this equation, we would have unbiased and consistent estimators. Now, the simultaneous equations can be consistently estimated using two-stage least squares. And what we're going to be doing here is very similar to what we've done in the previous presentation for instrumental variables. Only that now we have two equations, so we're going to be repeating the same procedure twice, once for each equation. So what we're going to do here is in the first stage, the endogenous variable would be regressed on the exogenous variables and the instruments from the other equation. And then in the second stage, what we're going to have here is that the endogenous variable would be replaced by the predicted values from the first stage, and the equations would be estimated by OLS. So again, exactly the same procedure for two-stage least squares when we have one equation, only that now we're going to be applying this procedure twice, once for each equation. Okay, so let's talk about how we will apply the two-stage least squares estimation. If we start with the structural equations, these are the equations that we have. And again, y1 appears here as well as here, and y2 appears here as well as here. And z1 and z2 are exogenous variables. So now, let's talk about Z2 being a good instrument for Y2. So this Z2 is actually a very good instrument for Y2. Why? Let's check the properties of a good instrument. First of all, Z2 is not in the equation for Y1, and that's true because it's not in here. But second, we have that Z2 is actually related to Y2, which is our endogenous variable. And so that's the second property of a good instrument. So that's why Z2, actually an exogenous variable, which is in the other equation, is a very good instrument for Y2. The same thing applies for Z1 being a very good instrument for Y1. Let's check this. Well, first of all, Z1 is not in the equation for Y2. You see, it's not in here. And because it's not in the equation for Y2, Z1 is also related to Y1 through the other equation. So this is, again, two of the properties of a good instrument. So here we have again Z2 being an instrument for Y2 and Z1 being an instrument for Y1. So let's apply the two-stage least squares. In the first stage, which would be a reduced form, we would be regressing the endogenous variable on all the exogenous variables and get the predicted value. So the first stage for equation 1, this is the equation 1, and that's the endogenous variable y2. So the first stage would be to regress this variable, y2, on the exogenous variable that we have in the same equation, as well as the instrument coming from the other equation, z2. And so now we could get the predicted values here, which is y2 hat. So the predicted values for the endogenous variable. Now, on the other hand, the first stage Now, on the other hand, the first stage for equation 2 would be to for the endogenous variable y1. So this is for the second equation. This will be the endogenous variable. So what we're going to do is we're going to be estimating a model now of y1, and then Z1 would be the instrument. So Z1 would be the instrument from here for Y1. And then we would still be including Z2, which is an exogenous variable here. So from these equations, we're going to be getting the predicted values that we have here. And then we would be estimating the equations by replacing y2 and y1 with the predicted values from the first stage here. And that's how the second stage of the two-stage least squares would work. And so again, this is the same procedure as the two-stage least squares for a single equation, only that we're repeating it twice for each equation. Okay, so let's give an example. So here we have the labor supply and demand for working women. And here's the labor supply equation for married working women, and that's going to be the hours worked. So the hours that women work would be a function of the wage that they receive, the log wage, their education, their age, the number of kids under 6 years old, and the non-wife income here. So basically, how many hours women are going to supply obviously depends on the wage that they could receive, um, but they also care about, like, do they have young kids at home, and how much is the rest of the income in the household as well. Now, the labor demand for married working women, this will be the wages offered by an employer. So here the wages offered are depending on the hours that workers are providing, obviously the education of the person, and experience and experience square. So now notice that, for example, if someone has young kids at home or what their age is, these are not determinants in this equation, because if they were, that would be discrimination of how much wage is provided. So wage is only based on education and experience in this case. So these age number of young kids at home and the rest of the income, they are not determinants on the for the wage as well. So because they don't occur in this equation here, actually they would be um, these variables here would actually be very good instruments that we have for log of wage right here for this equation, because they're related to the hours, which hours would be an endogenous variable here. So the same thing, but only in reverse. We have that wage, we have that experience is a determinant of log of wage, but not how many hours women are working. So therefore, experience and experience square, these two variables here can be used as instruments for hours. So what we are saying here is that we have structural equations. These are the two dependent variables, and they also come as independent variables. We have variable here that is repeated but assumed exogenous. And then we have these variables here that could actually serve as instruments for hours. And we also have these variables here, experience and experience squared, that could be instruments for the log wage here, which is an endogenous variable. So that's what we're going to be doing. Okay, so here are the structural equations again from the previous slide. So as we said, experience and experience squared are instruments for log of wage. So these two are actually instruments for log of wage because they're not in the hours equation and they're related to the log of wage right here through this equation. And then same applies for age, kids less than 6 years old, and non-wife income. So these three variables that we have here are very good instruments for hours here because they are not in the log of wage equation and they're related to hours, to the independent, to the endogenous variable. So to do two-stage least squares, the first stage we're going to be estimating the reduced form, and we would be regressing the endogenous variables on all of the exogenous variables to get the predicted values. So the first stage for equation 1 would be getting the endogenous variable here, log of wage, on the instruments of experience and experience square. So these two would be, as we said, the instruments, and these are still the exogenous variables. So we're going to be getting the predicted values. And the first stage for equation 2, right here, where ours is endogenous, we would be having a equation of ours that depends on age, kids less than 6 years old, and non-wife income. So these are actually going to be the instruments here. And then we're going to be having the exogenous variables here. Uh, okay, so now that we are estimating the reduced form equations, we're getting the predicted values. What we're going to do is go back into the original equations and here into the structural equations. And instead of using log wage and hours, we are going to be using log wage hat and hours hat. And that's how we're going to be getting the two-stage least squares coefficients here. Okay, so these are the results for the OLS and the two-stage least squares estimation. So this is for the first equation where we have hours being explained by the log wage. And so if we just do an OLS and we ignore the fact that we have endogeneity and simultaneity, here's what we're going to get. So hours is being regressed on log of wage, education age, kids less than 6 years old, and non-wife income. And what we're seeing here is that the coefficient here on log of wage is not significant. Okay, so now the two-stage least squares, the first stage would be, we would be regressing this log wage right here on the independent variables that we had here because they're exogenous, so we're going to keep them, but we will be using experience and experience squared. These are the variables that were in the other equation. We're going to be using them as instruments here, and so these are going to be the coefficients here as well. Okay, so now notice that these coefficients are significantly different from zero individually, which is a good thing because this means they're good instruments. If we actually do an F-test on joint significance on both of these coefficients, we are going to see that they're jointly significant as well. So again, good. These instruments are good. And the second stage, what it would do is we would replace in the hours equation, we would replace log of wage, which would not be log of wage, but the predicted values from this first stage here. And that's the coefficient that we're going to get, and we're going to keep all the rest of the variables. So even though how regression output looks like as if that's log wage, that's not log wage, that's log wage hat, is the predicted value coming from the first stage here. And this is the coefficient here. So notice now that the two-stage least squares coefficient is positive and significant, whereas here it was not significant. So the way we would be interpreting this coefficient is that for each percent increase in wages, the hours worked would increase by 16.4 hours for working women. And so what we are finding here is for the first equation, we are actually, if we ignore the simultaneity bias and basically we get bias coefficients here, we have not the coefficient that's not significant, but here the coefficient is significant using the two-stage least squares, the correct procedure. Okay. So now these are the simultaneous equations, but here we have for the second equation. So here we have log of wage regressed on hours, and these are the independent variables. So what we're seeing here is that this coefficient is not significantly different from 0. And so now by applying the two-stage least squares, the first stage would be the endogenous variable hours. This variable now is the dependent variable. And then we have all of the exogenous variables in here, but we also have the instruments. These are the instruments from the other equation. So these are the independent variables in the other equation: age, kids less than 6 years old, and non-wife income. So we're putting them here. We're noticing that we actually have 2 of the 3 coefficients are significantly different from 0. So this means that these are good instruments. If we do an F-test on all of these 3 coefficients, we're finding that these coefficients are jointly significant. So again, that's a good thing, that the instruments are related to the endogenous variable. So now we pick the predicted values, which is hours hat, and we put hours hat in here. So even though it looks like it's hours, that's now hours hat, and that's the coefficient on it. So now we are regressing log of wage on hours hat and all of the independent variables that are exogenous, and these are the results. And what we're finding here is that this coefficient in the two-stage least squares is also not significant. And so another thing to notice here is that these coefficients are very close to these coefficients. And so what this means that is perhaps we don't see a lot of endogeneity here. Certainly not like in the previous equation where we had change in significance of the main variable. We do not see this, this here for this equation. Okay, so finally we're going to talk about order condition and rank condition for identification. Basically, can we estimate the simultaneous equations with two-stage least squares, and what is necessary and sufficient conditions for it? So the order condition states that an equation is identified, which means we can estimate it, if at least one of the exogenous variable is excluded from this equation. But the rank condition, which is the sufficient condition, states that an equation is identified if and only if the other equation includes one of these exogenous variables that's excluded from this equation. So what does that mean? So if we have this simultaneous equations here, where we have y1 is here, and y2 is here and here, and this z1 and z2 are exogenous variables. For the y1 equation to be identified here, we need to have at least one instrument excluded from here. Well, I'm looking at z2 being excluded from here, and the rank condition said that it should be included in the other equation. So that's actually satisfied. And what we're noticing here also is that this is exactly the conditions for Z2 to serve as an instrument for Y2, which means it should be excluded from this equation for Y1. So basically Z2 is not a determinant of Y1. And also there's a relationship between Z2 and Y2. So it's included in this equation as well. So the conditions for the rank condition for identification is the same as us having a really good instrument Z2 for this endogenous variable here, Y2. And the same applies for actually Z1 being a good instrument for Y1. So z1 is excluded from this equation, and for y2, and z1 is also related to y1, which is the endogenous variable. So this is the rank condition for the second equation, is that the z1 is excluded from the second equation and is included in the first one. Okay, so let's discuss testing for the rank condition. So the rank condition states that exogenous variables that are excluded from the equation are included in the other equation, and this can be tested using the reduced form equation. So for the equation of y1 to be identified, so basically for us to be able to estimate it, is there needs to be at least one good instrument z2 for y2. So we need to have a good instrument z2 for y2. Well, what is a good instrument? If we estimate the reduced form equation, so this is the first stage equation, and we put in here z2, we need to test whether this coefficient here, delta 2, is basically significantly different from 0 or not. If it's significantly different from 0, this means that we have a good instrument for y2, and therefore the equation for y1 can be identified. And if this is not significantly different from 0, then z2 is not a good instrument for y2. So to use our example to test for the rank condition is for the equation for hours to be identified, there needs to be at least one exogenous variable that's excluded from the equation for hours and included in the equation for log wage. So let's estimate the reduced form equation for log wage. And so here we have log wage regressed on experience, experience square. So these two, experience and experience square, are the instruments for log wage, and these are now the exogenous variables which we can still put in this equation. And so this would be equivalent to testing for these coefficients of delta 1 and delta 2 on experience and experience square, whether or not they're jointly significantly different from 0. So here, if they're not, then the equation for hours would not be identified because we would not be having good instruments for it. And if they're jointly significantly different from 0, then the equation for hours would be identified. So in our particular example, if we do an F test, that's the F statistic, and the p-value is less than 0.05, so the coefficients are jointly significant. So notice that if this is the reduced form equation for log of wage, and these are good instruments for the log of wage, the other equation for hours is actually identified and can be estimated. So now doing the same thing for the equation of log wage to be identified, there needs to be at least one exogenous variable that's excluded from this equation for log wage and included in the equation for hours. So now we can estimate the reduced form equation for hours, and this is the reduced form equation. So here now this would be the instruments here for hours, and these are the exogenous variables. And here we would be testing if these coefficients on age, kids less than 6 years old, and non-wife income, if these coefficients are jointly significantly different from 0. So if they're not, then the equation for log of wage would not be identified. And if they are, then the coefficients for the equation for log wage would be identified. So this is the F statistic and the p-value, and what we are concluding here is that the coefficients are jointly significant. So what we are finding here again is that if these coefficients here are jointly significant, then they are good instruments for hours. And if they are good instruments for hours, then the other equation for log of wage would be identified and can be estimated. So as review questions, let's talk about what causes the endogeneity bias in simultaneous equations. Then describe the two-stage least squares procedure for simultaneous equations, and describe the rank condition and testing for the rank condition.